Okay, guys, I think we'll be starting now. I'll just share my screen. Okay, so the topic for today is segment trees, and this is a very versatile data structure. And the reason I chose this, I'll just give you a background, is because I myself was confused about how to use them and how to get them to work, and they keep appearing in really good contests like ICPC or Code Jam, Kickstart, Hacker Cup. And so I wanted to give a talk so that everyone can learn about them. So that's a bit of the introduction. Okay, yeah, so that's the basics, and a lot of what my talk about with the talk will be it's a lot of it is inspired from this page. This is the RU Max English translation, and I think this is a very good site for any competitive programming or any competitive programming algorithms or any other things like that. So you should definitely go and look at this after the talk. So I'll be using just some basic drawings. uh, right. So what are segment trees? So basically, you can think of them as something to make O of n operations into O of log n, especially range operations. So yeah, for example, let's say I have an array. I'll just remove this. Yeah, so let's say I have an array here, and I've been given this array. This array is given to me initially, and I want to do some range addition on this. So let's say add 5 to this, or subtract 3 from this. And at each time step, I have to do some kind of query. So after each time step, say I have to find the maximum of the entire array, or I have to find the maximum in some small range of it, or I have to find some one element individually. So let's say this is 5. So then it will become 10. It'll become 10 after the first update, and 7 after the second update. So I have to be able to support such queries. So this is what basically segment trees support, range queries. And the reason, so a very brute force way to do this would be just to go through all these elements of the array and add 5 and then subtract 3 from here, and then whenever a query comes, you just find the element here. But that would take O of n time per query. So I'd be going through all these, updating them plus 5, and then here -3. So that would take a lot of time, and that's not possible for most of the problems. So that's where segment trees come into play. Right. So let me just change this. Yeah. So I'll be sharing my implementation of segment trees. So the thing about segment trees is it's not just enough to know about the theory. If you can't code them up, then it's a big problem. So I'll be explaining that part too. Right. Okay. Just a second. Yeah. Okay. So first of all, let's just start with how segment trees are constructed. So given an array, the way it's constructed is it's like a tree. So you can think of it as a tree like this. It's always a binary tree. Segment trees are always binary. Just the thing is that each node corresponds to a given range. So and the root node always corresponds to the entire tree. This node corresponds to this part of the array, the first half. This node corresponds to the second half, and then this to the first quarter, the second quarter, the third quarter, and the fourth quarter. So this is
So
basically
what
how
does
the entire tree is built.
what does it store
Yeah,
in?
I'll come to that. So at each node, whatever function you want to output, the answer for that function on the range is stored. So I'll come to that. I'll come to what I mean by that. So let's say if the query is the sum query. So the problem given is given a range, say this range, there are some range updates. So say I have to do +5 here, -5 here, and finally I have to find the answer for the sum of all values in this range. Now this is very hard to do without a segment tree. I'll have to actually go here, go and add 5 to all these elements, subtract 5 from all these elements, and then find again the sum of all these elements. So what this does is, at each node I store the sum of this range. At this node I store the sum of this range. At this node I store the sum of this range. So we'll be going into how segment trees are built, and also how they are implemented. So I'll just get rid of this. Yeah. So basically this is how it is. So this is the entire array. This is one part. So the answer to the function, whichever function you want to compute, may be sum or maximum or anything like that. So that is stored here in the tree. So this is actually one node. You can think of it as a binary tree like this. Yeah. So okay, any doubts till now? Okay. So yeah. So how are we going to call this? Again, recursively. Now you can see my implementation is pretty much it's inspired by this post. So again, I advise you to check out this cpalgorithms.com, and it's an English translation of the Russian website, and that has really good algorithms, and the segment tree is also a good article over there. So that's that. And yeah, so now we'll just come to the implementation. So on this article, actually what I've noticed is they don't tell you the end, they don't give you the whole segment tree right away. They kind of build it up from start, like a very basic one, and then they add range updates and range queries and stuff. So I'll just give you the entire thing right now, so that you don't have to get confused, right? So okay, yeah. So what I like to use is I like to use a custom made segment tree, in the sense that each node in our array here, each node is a number, right? Like this, say 1, 2, 3, 4, things like that. But I like to take the whole thing as a node, my own custom made class node. So I'll tell you why this is, and this is really beneficial, and you'll get to know in a bit. So we can make this an int also. I mean, you can just remove all this and put int a, right? So some of the, wait, I'll just put another Google Drawings. Yeah. Okay. Yeah. Okay. So some of the functions, the kind of I don't know, operations you can say that segment trees support are two things. Basically, deep down, just two things. So one is uh, range update, and the other one is range query. So you'll have to get to know, I mean, you'll have to be familiar. I think you can, like, I'll make you familiar with these terms. So what do you mean by update and query? Update means change the value. So change the value at, say, all this entire range. So make all the elements here, increase them by 5, or set the value of at all these elements to 6, something like that. So this is an update query. And a range query itself is, query is like you're asking for something. So if I want to find the sum from here to here, the sum of all elements, so that is a query. Or I want to find the maximum from here to here, or I want to find the maximum and how frequently it occurs. So there can be many variations of this, right? So yeah, that's, and yeah, it's not just sum or maximum. You can use any custom made function as long as there's some properties of the functions. So as long as you can get the answer for the function if you know the left half of the function, the right half of the function. So sum is obvious. If I know the sum of the left half of the array and I know the sum of the right half of the array, I can obviously compute the sum for the entire array, which is basically the sum of these two. So if the function has that property that I can get the function on the total range if I know the function on each half of the range, then it can be used in the segment tree, right? So I'll just change that. Hmm. Okay, so I'll just give you a few functions that can be done. So one question is, given an array, there are obviously queries. So queries come in the form L, R, and say C. So on the range L to R, I have to add number C. So for each of these elements, I have to do plus C, plus C, plus C. So if C is 2, if this is 1, 2, 3, 4, it will become 3, 4, 5, 6, something like that. And also I have to find the how many times the maximum occurs. I have to find both the maximum and the frequency of the maximum. So this is just an example why I used this class here, a custom made class. So if that's the question given to me, what I will do is I'll just keep at each node at each node of the segment tree, I'll store the maximum in that range and the number of times the maximum occurs. So if the maximum is say 5 in this array and 5 occurs twice here somewhere and 5 occurs twice here, okay, 3 times here. So knowing the answer for this half and this half, am I able to compute the answer for the entire thing? Yes, because I'll check if the max over here is greater than the max here. Then if that's the case, then this itself is the max for the entire array. If the max here is greater, this is the max. And if the max are equal, the max here and here, then I'll add the frequency of both. So what I do is I keep two numbers, int max comma and frequency, right? So two things, and I'll also set up a constructor. Okay, yeah. So this is the node class. So each node signifies single one single node in the segment tree. So this whole thing is one node, this whole thing is one node. So the tree version of this is basically this. So that's the tree version. So any doubts till now? Guys. Okay. So
No, no doubts.
how many people are there? Okay. Okay. So I'll set up a constructor here. So that can be, yeah. So I'll make max is equal to say 0 and frequency. So this can be some simple constructor. Now, right now coming to range update, there's two possible varieties of this. So I think, yeah, I think did you guys understand this? So what I'll do is while combining this, I'll take the maximum from here, take the maximum from here, compare them, and basing on which one is the maximum, I'll decide the answer for the entire thing. So that's why it's very important to use a custom made merge function. So to merge this cell and this cell, to merge them into this cell. So both this cell will use the results of this cell as well as this cell. So to merge, you can write your own custom made merge function. So that is again one more advantage if you use a class. So I have in this class a merge function also. So the merge function will be if okay, left. So what I'm passing here, I'm passing two objects here of type node. Both are of type this type. And if left dot max is greater than right dot max, then I return uh, node of, I return left basically. Yeah. Else if the case is that this one is where I return right, else I return a new node. So I'll have to declare a node variable, node some temporary thing, and temp dot max is equal to this one. Since now both of them are equal, so it's this, and temp dot frequency is equal to the combined frequency of these two. So now you see how you can merge very easily if you have a custom made function. So that's what I've done here. Okay. So coming to, or I'll also explain all the functions now of the segment tree. So it has this class segment tree. It has a vector of nodes, and that's called T. T is for the tree, and L is for lazy. We'll come to what lazy means later. And again, marked also will come. You don't have to worry about this right now. So merges while constructing the tree. If I know the answer for this, and I know the answer, I mean I know the value here, I know the value here, and I want to compute the value here. So that's what merge is used for. So second is build. Okay. Yeah. Before that, yeah. So these are some public methods that I've made. So you can easily call the segment tree like this. So seg seg tree, I can just say a of some 60 or something. So I want a segment tree of size 60. If yeah. So I'll pass an array to this and the size of the array. So what this will do, it will resize this t. T is the vector of, so if you don't know what a vector is basically just an array. It's an array with some other functionalities. So it will assign the size for this, and it will call build. So I don't want to, these are like public functions. So these are the ones that the user can call. So the user is me itself, but it's more easy when I have it like this. So for query calls the internal query function. So update also calls the internal update function. Okay. Yeah. So now let's see what build does. So the way the segment tree is built is this. There are three parameters here: int v, tl, and tr. So actually, this tree is never stored like this. It's actually stored as an entire array. This tree, what you see here, is never stored as a tree because of obvious reasons. First of all, you have to get into linked lists and stuff, which gets nasty. So it's stored as an array. And I think you know how to store a, I don't know if you guys know, but the way to store a binary tree into as an array is keep the root here and the left child at 2v. So if this is index 1, so at index 2 is the left child, and at index 2 2x plus 1, I store the right child. So the right child is at 3. Same thing for here. So now the left child is here. The left child is at 2. The left child of the left child will be at 4. So this okay, wait, this is getting in the way. What happened? Okay, anyway. So this child will be here. The right child of the left child will be at 5. So I think you guys know the way to, I think you might have studied it in the class, the way to store a segment tree, the way to store a binary tree as an array. So that's what's basically done here. Okay, what's this? So that's what's happening here. This V stands for the index. So V is 1, 2, 3, and TL and TR are the ranges, left and right ranges of the tree. So now the way build is done is I first call build on the root node, that internally calls build on the two left children, and then it merges both of them into the parent. So I call build on this, I call build on this, and merge the answer here. So it's it's simple recursion. So look, the code is also simple. So if TL is equal to TR, and yeah, one more thing, TL and TR initially are passed as 1 and n. So you see build the start node is 1, so the index node is 1, and 1 and n are passed as ranges. So yeah, you guys can hear me, right? I think I might have had some problem.
Yes, you are audible.
Yeah, okay. So TL and TR are initially 1, 1 and n. So n is the size. So next, when I go here, I break it up into 2. So the midpoint. Then I call A 2v 2v plus 1. What I explained here. 2v 2v plus 1. So now I'm going to build this, so this and this. And Tm plus 1 Tr is, I mean, TL and Tm from left to the mid and mid plus 1 to the right. So actually it's a bit redundant to pass all three parameters here. So if I know V, actually I can calculate implicitly TL and TR. I should be able to, right? Because one is 1 to n. One signifies the range 1 to n. Two signifies the range 1 to mid. But I don't want to do that because if I pass everything, it becomes so much more easier. And then merge. So that's as simple as that. So let's see the update function. So, yeah. Just ignore this for now. Yeah. So update, when I want to update something, let's say I want to update this range. So I want to add 5 to all the numbers in this range. So what I'll do, ignore push also for now. That's later. So again, and now this function update and query. So there's basically just three main functions: build, update, and query. So the update function has 6 parameters. So the vertex v. So these three are again from the build, the same as the build. And now LR is the range to update, and that is not exactly that. That should be equal to TL and TR. So we're trying to find such TL and TR such that this range matches this range perfectly. So if the query is say, okay, this is a bit dirty. So the query is say update range 2 to 5. Update everything in the range of 2 to 5 with some value 5. So initially I will call the whole thing on 1 to n. So initially this will be 1 to n and this will be 2 to 5. This is the user, whatever the user wants, this one. And if I get them equal, well and good, I just return the value here. I mean, I just update the value here at T of v. Else, again I break it up into two parts and do the update and merge. So suppose the query is wait a minute. Yeah, yeah. So here is where the smart part happens. This max and min of this. So what's going to happen is if the range is just 2 to 5 and say the entire, okay, wait, if the range is 2 to 5 and the array is of 1 to n, 1 to some, let's take 7. So currently I'll look at both sides. Do I have to update both sides? Yes, there are, this is 7. Okay. So I have to update, and this is say the mid is 3 and 4. So there is some updates to be done on this side and some updates to be done on this side. So that means I have to call both of them. So I'll recursively call both of them. Suppose the query is just 1 to 3, 2 to 3, or say 1 to 3. I won't even bother calling this part because there's nothing to update here, right? And I'll have to update all the entire tree, all the till the depth of the tree till I reach these nodes. So that's what this does. So I find the mid, update 2 times this, and update 2 into 2 times this plus 1. That's also, this is the left child, right child. and this gets modified. So the reason there's min of r comma tm is because if whichever one is to the left, that's all I want. So if say the query here, I wanted the answer for some from here to here, so I'm just using kind of blocks to describe this. The min of this value and this value is this value, so I'll call this recursive query only here, only till here for this left part. For the right part, I'll call it here. So that's what this is doing. And then merge. So all this code is available here. I'll just tell you on this, on the cpalgorithms.com. I'll just tell you what are the nice modifications that I've done. So build is available here, update everything. Yeah. So yeah, so some nice problems that can be solved by segment trees are given here. So finding the maximum and the number of times set up here. So this is something I just did, right? So in the merge function, what I'm doing is left dot right. So again, wait, let's put this here. Yeah. So my node function stores max and frequency of the max. So I'm not storing a number at I'm storing, I mean, at each point of the tree. So in this tree, I'm not storing just one number, like say the max of all the entire tree. I'm storing the max, let's say it's 5, and I'm storing the frequency, how often it appears. So that's 4 maybe. So I'm storing both these things. Okay, maybe it's too dirty here. Time to make a new one. Damn. Okay, anyway. Yeah, so where was I? Yeah. And I check if any of them has the max itself right there, then I return the entire thing because the max will be same and the frequency also will be same. But if the max at both the left and right side are equal, then the frequency is the sum, and that's what I'm doing here. There's another nice one. So this is what basically. So even the GCD or LCM. So this also can be because this function, the function given is the GCD or LCM, that also has the nice property that if I know the LCM of all these numbers and I know the LCM of all these numbers, I can easily find out the LCM for all these numbers. So that's what's happening here. So here it would just be in here node, I'll just store one int LCM, and in merge, I'll just call LCM of left.lcm and right.lcm. Return node of LCM of left.lcm comma right of LCM. So that will give the LCM of the entire thing. So such functions can be easily done. So where is that from? Yeah. Okay, even this. Counting the number of zeros and searching for the kth zero. So this also can be done. So in their implementation, the one thing I found is they actually don't keep a separate node variable, node class, which so they make this as uh, pair int, or they just make this as int, things like that. So it's best to make your own custom made node function which stores the answer for any general query. And I'll come to one interesting problem later also. So that had a really good intuition behind it. Yeah. So there are many functions here. So find the smallest number greater than or equal to a specified number. So many such things can be done with using many such functions can be computed in OF login time using segment trees. So I recommend you to read this article also. So it's really useful. And yeah, any doubts till now? Any doubts, anyone? Guys, ask some doubts, please. It'll be boring if I just talk the entire time. Okay, maybe probably think of some doubts to ask later. Okay, so So I just went through the entire implementation of the segment tree. Uh, so yeah, so even there's something called descending down the tree. So not always the answer is right there at a, is not always the answer is a range query, right? So it's not always the answer. The question given to you is find the sum of all the nodes here, find the sum of all values here, or find the sum of all values here. So they can ask you things like find the kth zero, or find the the kth element greater than some x element. So for that, it's enough to just descend down the tree. You see what I mean? So I'll in each node, I'll store the number of zeros there. And if I have to find the fifth zero, when I'm at root, I'll see here if there are more than 5 zeros or less than 5 zeros. If it's less than equal to 5, I'll just descend down this part. And if it's greater than 5, yeah, if it's less than 5, I'll descend down this part, sorry. And if it's greater than 5, I'll descend down this. So that's it. So this is descending down the tree. That's another function. So I mean, I can share this entire code with all of you. That's not a problem, right? And yeah, there's one interesting thing in query, especially in query. So in query, the way the implementation that I saw here works. So if you go to any query function, okay, what happened? Yeah, am I audible, guys? Am I still audible? Just confirm.
Yes, you're audible.
Yeah, okay. Okay, so any query function, okay, where's query function?
Are you sharing a screen? Like we can't see your screen, but
Oh, you can't see my screen.
no.
Okay, I'll share it again. Now?
Yes, we can see it now.
Okay, okay. I think I pressed something by mistake. So there's some nuances in this. So what this merge does is I don't know if you might be able to understand the entirety of it right now. So again, I urge you to go read that. But the way this does is what this does is it doesn't exactly find out while descending down the tree, it doesn't exactly find out which part to descend to. So it kind of like descends into both this query function. So because it's easier to implement, there's nothing else. And if there's a descent such that that part is not required, so say the query is only till here and I'm at the root here, and now I have to descend only to this part, right? I don't have to descend to this part. Okay, this is too dirty. Let's change this. Let's make another drawings. Mm-hmm. Okay, so if the query that I want to do, like say find the sum of this, if it's only here, I don't have to descend down both parts of the tree, right? I just have to go here. But the way this is implemented is it goes down both, so it's easy to write all in one line. So you see return merge of query of left part. It's a recursive function. This is a query function and it's called again here, and query of the right part. So that's what it's doing. And if there's some extraneous calls, so this will call both, and this call will be made in such a way that its L becomes greater than R. So this is smart part that I told you about what's happening here. L to min of RTM. Okay. And TM to TR, and yeah, TR to max of max of L comma TM plus 1 comma R. So it's a bit hard to explain what exactly is going on, but if you just, if you just draw a segment tree, you can figure it out. And yeah, so I encourage you to do that. And if there is this condition holds, that means I'm returning from here. I just called this, and this was an external call, which is not actually required. So okay, seems to be some problem. Can you guys hear me by any chance? Okay.
Yes, yes.
Okay, no, it's fine. Yeah, I'm having, might be facing some issues, guys. Sorry about that. Yeah, so if L is greater than R, so that's done by this smart thing. So this will make sure this part. So this is the LNR required. This is the LNR of the current range, right? That's what I explained to you. And this is the vertex of the tree. So the vertex is this vertex. So this will make sure that such extraneous calls like this, if the range, the required LNR are only here, I'll still end up calling both, but I'll make sure that for this call, L is greater than R. So then what I do is I return something called no merge. No merge is the identity, the function identity. So I think you might have studied what is the additive identity. The additive identity is 0. So if I'm trying to find the sum of this range, and I call find sum of this plus find sum of this. So, and this will also further call this and this and this, right? So I want this to return something that won't mess up the merge. It will be as good as just calling this. So that's the identity function. So the additive identity is 0. So what no merge is here. So node no merge, and I'll just make that as 0. Node is 0. Okay, where's the constructor? Okay, I just remove the constructor. Not LCM. Sum. So this can be for sum, let's say. So no merge will be 0. So I'll return a 0 from this. So that's the specialty of using this no merge. And yeah, other than that, I think I've covered the basics. So let's go to the uses of segment trees. So segment trees are most of the times. Okay. So segment trees are most of the times used to combine two or more than two such functions. So one is uh, range assign. Oh damn. Okay, plus range query. And when I mean query, it can be any of those functions which has that property that if I know the left part and the right part, I should be able to merge, which has the mergeability function property. Or range update. I mean, sorry, range add subtract. So so this part has some extra thing. So for these two, and yeah, one more note to everyone. So if you are competitive programmers, if you're aware, okay, right, yeah, if you're aware of something called a Fenwick tree, you know, if if the requirement of the problem is to do a range add or subtract, along with that a range query for just simple sum. So basically the thing is given an array, some they'll be given some ranges to update, subtract, update in the sense subtract or add, and then I have to find the sum for some other range, and everything should happen in O of log n. So that's the thing about segment trees, everything happens in O of log n, and build happens in O of n log n. Right. So for that, use a Fenwick tree. So if you don't know what a Fenwick tree is, read about it. But it's way simpler. It's like just few lines of code, and it runs faster too. So for such things, use a Fenwick tree. Don't use a segment tree. If only it is range add and range sum. For range add and range sum, use Fenwick trees. But if the function is say things like max, then you can't use Fenwick trees, or the max plus frequency of max plus frequency of max. Or they can be like, they can be really complex functions, a problem of which I will show you. Okay. Yeah, so range assign. So range assign uses something called a push function. It's another just subroutine. So, okay, before that, any doubts? Anyone? Anyone have any doubts? Okay, no one has any doubts. Fine, I'll just continue. Okay, so the push function. So what I'm going to do is, for range assign, again, this is also something really nice. Yeah, so now let's just make a segment tree here. And yeah, so if the query is assign number 5, so just erase all the from 1 to 6, let's say, and this is till 10. So from 1 to 6, make all the elements of the array as -1. And I have to do it in of login. So I can't go and make everything as -1. So the way to do it is, it's again recursive. So I'll call this part. I'll look where the range is. 1 to 6, does it fit? Does it go here? Does it go here? Or this is the entire thing. It's not here. It goes to both places because 6 will be around somewhere here. So I can make 2 recursive calls. Now here, you see this range is 1 to 5. 1 to 5. And this entire range is being updated. So what I'll do is, I'll set a flag, a mark here. So that's the marked array. And I'll make marked equal to 1. So what marked equal to 1 will do is, it's like magically assigning number -1 to all the elements here. So at this node, I'll put -1. So so note that this thing is not an array. This is just one node. Like making a segment tree, it's like this. So this is just one number. There's just one number here. There's one number here. There's one number here. And this number is the function value applied to this range. This number is the function value of this range. So the function value over here, if I'm storing the whatever sum, or if I'm storing the max, or if I'm storing the max, it'll just be 5. If I'm storing the sum, it will be 5 into the range. So, and I'll do something called marked. Marked means this vertex is marked. If in future any query comes, like find the sum from here to here, I'll only descend up to a marked vertex. Below a marked vertex, I won't descend because this was already updated as 5. So actually these elements won't be updated as 5. So these elements, if if you merge all this, you won't get this because this was just marked. So this was like saying, okay, don't go further down, whatever the answer is right here. So something like that. So that's what push does. So what push does is, if it's marked, okay, wait, yeah. So yeah, sorry, not push right now. There's update. Yeah. So this is the update with the lazy and the mark. So you see what I'm doing? If I find the range, if L is equal to TL and TR is equal to R, so if the expected range and the current range I'm at are equal, I just simply assign the new value to this. And I set this as marked. So marked means I don't want to go further down the tree. I just end it here. Right. So and while querying, Yeah, so wait, we'll cover that. And the other one was, where is that one? Okay, so that was the assigned thing. So while querying, if I get a marked vertex, I'll never go below that. If I find out a vertex mark, the answer is right there. So that's the answer. I won't go down searching for it more. Right. So the other part of this is range update. So range update is adding 5 to all these elements. Yeah. So for that, what we're going to do is create a lazy tree. Okay. So lazy tree, wait, yeah. So a lazy tree is another tree that mirrors the main tree. That's it. So this is a normal tree. I'll be creating a lazy tree. So lazy tree is just another tree, and this will just store the updates. So let's say that this is 1, 2, 3, 4. Okay, so and it's a sum function, 1, 2, 3, 4. So what will this have? This will have just 1, 2, 3, 4, the individual nodes. This will have 2 plus 1, 3. This will have 3 plus 4, 7, and this will have 10. These are the values stored in the segment tree. Okay, and if I want to say update range 1 to 2 with 5, add 5 to this. So what I'll do is I'll go down this lazy tree, find the query for 1 to 2, find all the nodes that query for 1 to 2, and just simply add a 5 in them. So this means that this 5 is actually lazily added to these elements. So I'm not going down all the way to the elements to add, I'm just adding it here. So if the thing is, the query is 1 to 3, add 5. So I'll add 5 here and here. So for this I had to go down, but here I saved time going all the way down to the nodes. And again, for querying, if I get a node, if I'm querying for this node, I'll add up I'll take the value here and keep adding all the values of the lazy tree. So if there's another update, say 1 to 4, add 10. So I'll just find 1 to 4, add 10 here. Now I'm asked find a of 1. So what will a of 1 be? A of 1 will be 1. Then I'll find the corresponding in the lazy, 1 plus 5 plus 10. So that will be the actual a of 1. So that I can return that. Yeah, so I think it's 6:30 already. So we have maybe 15 more minutes. And that's what this push does. Mm-hmm. This is the same one. Yeah, this one does. So that updates only till here. So that's basically, I don't traverse the entire tree. You see, the tree might be huge. It might be here, here, here. So if I get this range, I just update 5 here. So that's it. Okay, so I think yeah, before this, any doubts, guys? Anyone? Okay. So I'll just end it with one problem. That's it. Okay, so as you can see in this one, you have to find the best alternating sum. So I mean, the problem's a bit long, but yeah, the gist of it is find the highest alternating sum, which is, so the array could be, so I'll just show you my submission also of it. Yeah. So the array could be this, and I have to find the best alternating sum in 1 to 2, 6 to 7, 3 to 4, 1 to 2, 2 to 3, all these. So this is a query, and So what I did here is, so it's not trivial to see how a segment tree can be used in this. So the solution here is, you store, at each node you store the best alternating, uh, I mean, what should I say, alternating series, starting, because now you don't know where to take this minus and where to take this plus, which element should be minus, which element should be plus. If you're just given a random array, you don't know where the best subarray starts, of best alternating subarray. By best I mean by which has maximum sum. Yeah. So you just take a general case where anything can start with a minus or a plus, and that's what's done here. So this one used that node function really well. So what I did is, here it starts with a I just made a custom node function that stores 4 values. The best subarray which starts with a minus, ends with a minus, starts with a minus, ends with a plus, and this is how I've made an this is basically the way I've done it, implemented it. So these 4 values are stored, and these 4 can easily be merged. So this is the merge. So I just store the maximum each time. So I can merge something that ends in a minus and starts with a plus. So if something ends in a minus, so there is this range here that ends in a minus, and then there's this range that ends in a that starts with a plus. So these two can be merged, but something that ends in a minus and starts in a minus, that can't be merged. So yeah, this is just one problem. And I think the time is also a bit it's 6:30 now. So again, any doubts, I'll ask. If you don't have any doubts, then we can end the session. And also I can share the code, share my implementation to whoever wants it. So I mean, I don't think there's a way to share in here, but if you can just DM me, and I'll share it with you, my implementation of segment trees. So yeah, I guess anyone have any questions? Yeah, I'll just check the YouTube also if there's any questions. Okay, wait, someone had put up a question in YouTube. In merge, should we return temp the new code generated? Okay, I didn't understand this. Okay, Ritvik Ganesh, are you still there? Okay, you asked it 6:09. Damn, it's already 6:30 now. Okay, wait, let me just try to find out. So in merge, should we return temp or the newly created? Okay, you mean, yeah, you should return temp, right? I didn't do that. Temp is the newly created node, right? Yeah, in the merge function. That's what I'm in the merge function. So temp is the newly created node. So I don't know what you mean by should we merge, should we return temp then newly return. Okay, yeah. So you mean I hadn't returned this? Yeah, you're right. Nice catch. Yeah, because it's a node return type. Yeah, I guess I missed this. Okay, yeah, thanks for pointing that out. So any other questions? Okay, I wasn't checking questions on YouTube chat. So anyone on YouTube chat, you can ask me questions if I have any. So I hope you guys understood the advantage of using this customly built node variable. So this lets you store whatever you want. Okay, can you also explain the build's base case? Okay, build is basically building the segment tree. So given the array, so the public version of this, so I like to use this. So this is very clean. Just build given array and n. So I assign n, I resize this, and resize this. And I do build a 1 1 1 1 n. So 1 is the node size, is the node index. So this, if you remember this drawing, this is the way to store a binary tree in an array. So at node 1 here, the children are left child at 2v, right child at 2v plus 1, right? So that's, so this is that, this is 1, and the range is 1 to n. So actually these two are kind of redundant. I don't need to actually, in a function, these two can be calculated if I just know 1. If I know 1, 1 signifies the top node. So using some mathematics, some smart mathematics, I can get, given 1, I can get the range 1 to n. Given 2, I can get the range 1 to mid, because 2 is 1 to mid. 4 is 1 to the quarter. 3 is mid to the end, mid plus 1 to the end, because this is the right child. So, but it's better to pass everything in this itself, because that makes everything so much more easier. So you see, in build, what I'm doing is build the same array A, 2v. 2v is the left child, TL and TM. TL is the left tree boundary and TM is right tree boundary. I mean, TM is the mid, sorry, which will be the new right boundary. So the new right boundary will be mid here. And then 2v plus 1, mid plus 1 to R, and simply merge TV. So at that vert at V, so at 1, 1 will be the merge of 2 and 3. So this will be 2, this will be 3, this will be 1. So 1 will be the merge of this. So if the query is to find max and frequency of max, if the if 2 has, say the max is 5 and frequency is, frequency max is 5, frequency is 8, in the node 3, that is the left half, max is 5 and frequency is 2. So this merge, what it'll do, it'll check this doesn't satisfy, this doesn't satisfy, it'll create a new node. The max of this will be 1 and the frequency will be the frequency of the sum, so that will be 10, and so the value at 1 will be 510. Okay, so yeah, any other doubts? On YouTube you can ask, or if you're here you can unmute yourself and ask. I'll just wait for 2-3 minutes, and if there's no doubts then I'll end it. Okay, I guess there are no doubts, so yeah, we can end the talk. So if you guys want my code, or you want any detailed explanation to any of the things, or yeah, basically first of all I would recommend you to read that article, and also if you want to know all the small nice changes that I've made to that, like making a custom built segment tree and using this no merge, and there are a few other things like in push, and I didn't have time to explain all that perfectly. So if you have any doubts or you want my code or anything like that, just ping me. So I guess yeah, that's it.